Picture this, an endless sea of darkness, so vast it makes the deepest corners of our oceans seem like a puddle. Out there, in the unimaginable stretches between galaxies, lies a realm that defies everything we think we know about space. It's not just empty, it's not just silent, it's a cosmic frontier teeming with secrets, where particles thinner than a whisper and forces beyond our comprehension shape the very fabric of the universe. This is the intergalactic medium, and it's anything but ordinary. We often think of space as dotted with stars, planets, and galaxies' bright islands in a dark ocean. But what about the ocean itself? The space between galaxies isn't just a void. It's a dynamic, mysterious expanse filled with invisible matter, faint radiation, and structures so enormous they warp our understanding of scale. Scientists once believed these regions were nearly empty, but now we know they hold clues to the universe's grandest puzzles, from the nature of dark matter to the origins of the cosmos itself. So why does this matter to you? Because this isn't just about distant galaxies or abstract science. It's about pushing the boundaries of human curiosity. Every discovery in these uncharted realms reshapes our place in the universe, reminding us how much is still out there, waiting to be uncovered. And today, we're diving deep into that unknown. Together, we'll explore the hidden forces at work in the cosmic void, unravel the strange phenomena that challenge even the brightest minds, and uncover why the space between galaxies might just be the most fascinating place you've never imagined. Strap in, this journey is about to redefine what you thought was possible. The cosmic web is like the universe's hidden skeleton, an intricate, invisible framework stretching across the cosmos, holding everything together in ways we're only beginning to grasp. Picture the largest spiderweb you've ever seen, then multiply its size by billions, and you'll start to get a sense of this mind-bending structure. But instead of silk, this web is woven from dark matter, that mysterious substance we can't see but know exists because of its gravitational pull. These filaments act like cosmic highways, guiding galaxies into clusters and superclusters, shaping the universe as we know it. What's truly astonishing is how delicate and yet how powerful this web really is. The filaments between galaxies are so sparse that a single cubic meter might contain just a handful of atoms, far emptier than any vacuum we could create on Earth. Yet, over billions of years, gravity has sculpted these faint trails into the universe's grand design. Supercomputer simulations show how matter, pulled by dark energy and gravity, slowly clumps along these threads, forming the glowing cities of stars we call galaxies. Without this hidden architecture, galaxies would scatter randomly like leaves tossed by the wind. Instead, they gather along these invisible lines, clustering in ways that reveal the web's influence. And here's the wildest part: we're not just observers of this cosmic tapestry, we're part of it. Our own Milky Way sits at the intersection of filaments, connected to a vast neighborhood of galaxies, all moving in sync with the web's unseen currents. By studying these patterns, astronomers can trace the history of the universe itself, uncovering clues about how dark matter shaped everything from the first stars to the giant voids between galaxy clusters. The deeper we look, the more we realize the true story of the cosmos isn't just written in the stars, but in the silent, sprawling spaces between them. But here's the twist: dark matter isn't the only hidden player shaping the universe. While it weaves the cosmic web, another invisible force fills the voids between galaxies, searing hot gas, so thin it's barely there, yet so vast it holds answers to some of astronomy's biggest questions. Imagine a fog so diffuse you could fly through it for millions of years without noticing, except this isn't water vapor. It's plasma, superheated to millions of degrees, shimmering with the faint glow of X-rays. This is the intergalactic medium, and it's anything but empty. Scientists first detected this ghostly gas by accident. While studying distant quasars, they noticed something strange. Their light wasn't just traveling uninterrupted through space. Instead, it carried faint fingerprints like shadows cast by an unseen hand. Those shadows revealed a hidden ocean of ionized hydrogen and helium, remnants of the Big Bang, stretched so thin that a single teaspoon of it would contain just a few dozen atoms. Yet spread across billions of light years, this gas outweighs all the stars in the universe combined. What's truly mind-blowing is how this gas behaves. Unlike the orderly swirl of galaxies, it's chaotic, a turbulent sea stirred by supermassive black holes and exploding stars. When galaxies collide, they eject colossal waves of this material, like tsunamis in space, redistributing matter across the cosmic web. And here's where it gets even wilder. This gas isn't just floating passively. It's a cosmic recycling plant. Over eons, gravity pulls it into denser filaments, where it cools and collapses, birthing new generations of stars and galaxies. The very atoms in your body might have once drifted through these voids, part of an endless cycle of creation and destruction. Yet for all its importance, this gas is devilishly hard to study. It doesn't glow like stars or cast shadows like dark matter. Instead, astronomers rely on ultra-sensitive X-ray telescopes and subtle distortions in background light to map its presence. Each new observation peels back another layer, revealing how these vast, invisible reservoirs shape the evolution of the cosmos. So the next time you look up at the night sky, remember the real action isn't just in the glittering stars. It's in the silent, scorching depths between them, where the universe's hidden machinery keeps turning. Now let's zoom in on that ghostly ocean of ionized gas, the intergalactic medium, where temperatures soar to millions of degrees, yet the space is so empty it makes Earth's hardest vacuums seem crowded. Picture a single atom drifting alone in a room the size of a football stadium. That's the staggering scale of sparseness we're talking about. But don't let its faintness fool you. This plasma, mostly hydrogen and helium left over from the Big Bang, is the universe's hidden scaffolding, shaping galaxies in ways we're only starting to decode. X-ray telescopes have pulled back the curtain on this elusive material, capturing its faint glow like fireflies in a cosmic night. These observations reveal something astonishing. The gas isn't spread evenly. Instead, it clumps along the filaments of the cosmic web, pooling around galaxy clusters like dew on a spider's silk. Some of it even rains back into galaxies, drawn by gravity, where it cools and condenses into the fuel for new stars. It's a slow, billion-year process, nature's way of recycling the building blocks of creation. But here's where things get even more dramatic. Black holes, those infamous cosmic disruptors, are stirring the pot. When supermassive black holes at the hearts of galaxies gobble up matter, they don't just sit quietly, they belch out titanic jets of energy, heating the surrounding gas to unimaginable temperatures. These outbursts can blast material clear out of galaxies, pushing it back into the intergalactic medium like a cosmic pressure washer. In some cases, they even carve vast bubbles in the gas, leaving behind voids that echo with the violence of their birth. Yet this isn't just destruction, it's a delicate balance. Without these explosive feedback loops, galaxies might grow too fast, devouring all their gas in a frenzy of star formation. Instead, black holes act like cosmic regulators, their outbursts keeping the system in check. It's a dance of chaos and order, where the very forces that tear the universe apart also give it structure. And every time we peer deeper into these invisible realms, we uncover another layer of the grand, interconnected story where even the emptiest spaces hum with the secrets of existence. At the heart of nearly every galaxy, something extraordinary is happening. A supermassive black hole, millions or even billions of times heavier than our Sun, is unleashing unimaginable power. These cosmic monsters might seem like destroyers, but they're actually master regulators, shaping the fate of entire galaxies and the space between them. When they feed on surrounding gas and dust, they don't just swallow it silently. Instead, they erupt, shooting out jets of energy so intense they can outshine every star in their galaxy combined. These aren't just flashes in the pan, they're galactic winds, capable of blowing gas clear out of their home galaxies and into the vast intergalactic void. Think of it like a cosmic pressure valve. Without these outbursts, galaxies would gorge themselves on gas, forming stars at a frantic, unsustainable pace. But when a black hole fires up, its energy heats the surrounding material, pushing it away like a scorching wind. Some of this gas escapes entirely, joining the intergalactic medium, where it might eventually cool, collapse, and seed new galaxies elsewhere in the cosmic web. Other material gets pushed to the galaxy's outskirts, creating vast reservoirs that could fuel future generations of stars. It's a balancing act on a galactic scale, where destruction and creation are two sides of the same coin. The sheer scale of these winds is hard to fathom. They can stretch for hundreds of thousands of light years, carrying enough energy to reshape entire galaxy clusters. Astronomers have spotted their fingerprints in the X-ray glow of distant galaxies, where hot gas billows outward like smoke from a wildfire. In some cases, these outflows are so powerful they carve enormous bubbles in the surrounding intergalactic gas, leaving behind cavities that persist for millions of years. But here's the real kicker: these black hole winds don't just influence their immediate surroundings. They're part of a much larger cosmic recycling program. The atoms they eject might drift for eons, but eventually gravity pulls them back into the dance. Some could end up in entirely new galaxies, while others might circle back, completing a journey that spans billions of years. It's a reminder that in the grand scheme of the universe, nothing truly disappears. It just changes form, moving through an endless cycle of dispersal and rebirth. And that's the beauty of it. These violent, explosive events aren't just chaos, they're part of a finely tuned system that keeps the universe in balance. Without them, galaxies would burn too bright and too fast, exhausting their fuel before new stars could even form. Instead, black holes act like cosmic architects, shaping the destiny of galaxies and the spaces between them in ways we're only beginning to understand. So the next time you hear about a black hole's destructive power, remember, it's not just tearing things apart, it's helping to weave the fabric of the cosmos itself. Stars don't just live and die quietly, they go out with a bang, and that explosion sends ripples across the cosmos. When a massive star reaches the end of its life, it doesn't fade away. It detonates in a supernova, one of the most violent events in the universe. In a matter of seconds, the explosion unleashes more energy than our Sun will produce in its entire lifetime, blasting the star's outer layers into space at incredible speeds. But here's what's truly remarkable: those scattered fragments aren't just debris. They're the building blocks of everything around us, from planets to people. Inside stars, nuclear fusion forges heavy elements like carbon, oxygen, and iron. Without supernova, those elements would stay locked away forever. Instead, the explosion flings them far and wide, enriching the surrounding space with the ingredients for rocky planets, oceans, and even life itself. Some of this material drifts between stars, eventually finding its way into new generations of stellar nurseries. But a fraction escapes entirely, catapulted out of its home galaxy by the sheer force of the blast. These rogue atoms become cosmic wanderers, joining the sparse gas of the intergalactic medium, where they mix with the primordial hydrogen and helium left over from the Big Bang. Over billions of years, this process has transformed the universe from a simple soup of light elements into a chemically diverse tapestry. The first stars were pure hydrogen and helium, but today's stars, and the planets orbiting them, contain everything from lithium to gold, all forged in stellar furnaces and scattered by supernovae. Even now, the intergalactic medium is being subtly enriched as metals from countless explosions diffuse through the cosmic web. Future galaxies forming in these regions will inherit this chemical legacy, their stars born with a richer mix of elements than their ancestors. Yet this grand recycling system isn't perfect. Some of those heavy elements vanish without a trace, contributing to one of astronomy's biggest puzzles, the missing Baryon problem. Ordinary matter, the stuff we're made of, seems to be in short supply when we tally up all the visible stars and gas in the universe. The rest might be hiding in the intergalactic medium, so hot and diffuse that our telescopes struggle to detect it. If so, supernovae aren't just sprinkling metals into the void, they are helping us track down the universe's lost matter, one atom at a time. So the next time you look at a twinkling star, remember, it's not just a distant light. It's a future supernova, a chemical factory, and a cosmic recycler all in one. And the space between galaxies, far from empty, it's a reservoir of stardust, quietly waiting to be part of something new. Imagine counting all the atoms in the stars, planets, and galaxies you can see, and realizing you've only found half of what should be there. That's the baffling mystery astronomers call the missing Baryon problem. Baryons, the particles that make up ordinary matter like protons and neutrons, account for just 5% of the universe's total mass and energy. But here's the kicker. When scientists tally up all the visible stars, gas, and dust, nearly half of those baryons are nowhere to be found. It's like reading a cosmic grocery list where someone's crossed off half the items without explanation. So where did it all go? The leading suspect is hiding in plain sight, or rather, in near invisible sight. The warm-hot intergalactic medium, or WHIM, is a ghostly network of gas filaments threading through the cosmic web. This material is so hot it glows faintly in X-rays, yet so diffuse that a single cubic meter might hold just a few hundred atoms. It's the universe's ultimate hide-and-seek champion, blending into the background so well that even our best telescopes struggle to spot it. But when astronomers add up the potential mass of this elusive gas, the numbers start to make sense. Those missing baryons might not be missing at all, they've just been masquerading as empty space all along. Detecting the WHIM is like trying to find a whisper in a hurricane. Traditional telescopes see right through it, so scientists have to get creative. Some hunt for subtle distortions in the light of distant quasars, as WHIM filaments absorb specific wavelengths like cosmic fingerprints. Others use X-ray observatories to catch the faint glow of million-degree gas. Recent breakthroughs, like the detection of oxygen ions in the WHIM, have turned theoretical guesses into hard evidence. But the real game changer is coming. Next-generation telescopes, like the European Space Agency's Athena mission, will scan the skies with unprecedented sensitivity, potentially mapping this hidden matter in detail for the first time. Solving this puzzle isn't just about balancing the universe's books. It's about understanding how matter flows between galaxies, how structures form, and even how the cosmic web evolved. Those missing baryons are the universe's hidden scaffolding, and finding them could rewrite our story of how everything, from the tiniest atom to the largest galaxy cluster, came to be. And speaking of hidden forces, there's another invisible player shaping the voids between galaxies and magnetic fields. Far from empty, these stretches of space crackle with energy, their secrets waiting to be unraveled. Stretching across billions of light years, threading through the cosmic web like invisible wires, magnetic fields silently shape the universe in ways we're only beginning to understand. These aren't the strong, concentrated fields around stars or black holes, they're faint whispers of magnetism, so weak that a simple refrigerator magnet could overpower them. Yet their scale is staggering, weaving through the emptiest regions of space, where just one atom might drift alone for miles. How did such fragile forces come to span the entire cosmos? The answer might lie in the universe's chaotic infancy, when the first galaxies were still forming. Some theories suggest these fields were born from turbulence in the early universe, like ripples in a pond, but on a cosmic scale. As primordial plasma swirled and collided, tiny magnetic fields could have been stretched and amplified, eventually imprinting themselves across vast intergalactic distances. Others propose that galactic winds and jets from supermassive black holes pumped magnetism into the void like cosmic bellows, seeding the space between galaxies with these invisible lines of force. Whatever their origin, their presence is undeniable. When high-energy particles called cosmic rays zip through space, their paths curve ever so slightly, a telltale sign of magnetic influence even in the deepest voids. Detecting these ghostly fields isn't easy. Traditional telescopes see right through them, so astronomers rely on subtle clues. Radio telescopes catch the faintest whispers of polarized light, its orientation twisted by magnetic fields like a compass needle aligning to Earth's poles. In some regions, these fields appear to align with the cosmic web's filaments, as if tracing the universe's hidden skeleton. Their effects might seem minor, barely nudging a particle here or there, but over billions of years, these tiny nudges add up, potentially guiding how galaxies cluster and how gas flows between them. What's truly fascinating is how these fields defy expectations. In the emptiest parts of space, where matter is almost non-existent, magnetism persists like an echo of ancient chaos. Some researchers think they might even trap heat, preventing the intergalactic medium from cooling too quickly, a cosmic thermostat helping regulate star formation across the ages. Others speculate they could channel high-energy particles, creating invisible highways for cosmic rays. Yet for all their subtle power, these fields remain one of astronomy's great puzzles. How do they maintain their structure across such vast, empty distances? What role do they play in shaping the universe we see today? Each new discovery peels back another layer, revealing a cosmos far more intricate than we ever imagined, where even the emptiest spaces hum with invisible energy. And if you think that's mind-bending, wait until we venture into the coldest corners of the universe, where temperatures plunge to just a whisper above absolute zero. Somewhere in the constellation Bowotes, there's a hole in the universe so vast it could swallow thousands of Milky Ways without a trace. This is the Bowotes Void, a cosmic desert stretching 330 million light-years across, where galaxies are so scarce you could fly for millions of years without seeing a single one. If the universe is a bustling city, this void is its loneliest ghost town, a place where the rules of cosmic neighborhood planning seem to have been forgotten. What makes this void so baffling isn't just its size, it's what's missing. In a typical slice of space that large, you'd expect to find at least 2,000 galaxies. Here, astronomers have counted fewer than 60. That's like expecting a crowded stadium and finding just a handful of people scattered in the stands. The galaxies that do exist here aren't clustered together but float like isolated islands, separated by gulfs of darkness wider than most galaxy superclusters. So how did this cosmic emptiness come to be? One leading theory points back to the universe's infancy, when tiny quantum fluctuations in the primordial soup of matter and energy eventually grew into the large-scale structures we see today. Most regions had slightly denser patches that collapsed into galaxies, but the Bowotes void might have started as an unusually smooth pocket, a place where those initial ripples were barely a whisper. Over billions of years, as gravity pulled matter into filaments and clusters, this region never got the memo, remaining a fossil of the universe's most barren beginnings. But there's another, wilder possibility. What if something invisible is at work? Some researchers speculate that exotic physics, perhaps interactions with dark energy or undiscovered forces, could have sculpted this void intentionally. Others suggest it might be evidence of a collision with another universe in the multiverse, though these ideas remain highly speculative. What's certain is that voids like Bowotes aren't just empty space, they're laboratories for testing our deepest cosmological theories, places where the universe reveals its quirkiest behavior. And here's the twist, these voids aren't entirely lifeless. The few galaxies stranded in the Bowotes void have had to adapt to their desolate surroundings. With fewer galactic neighbors to disrupt them, they've evolved in isolation, some becoming oddball field galaxies with unusual shapes and star formation rates. It's as if they've been marooned on a cosmic island, forced to make do with limited resources. Yet even here, in the emptiest place we know, the universe finds a way to surprise us, proving that no corner of space, no matter how barren, is truly without its secrets. Studying voids like Bowotes does more than satisfy curiosity. It sharpens our entire understanding of cosmic structure. By mapping where galaxies aren't, astronomers can trace the invisible scaffolding of dark matter that shapes the universe. These voids also stretch our theories to the limit, forcing us to ask whether we've missed something fundamental about how gravity works on the largest scales. Every time we peer into these cosmic deserts, we're reminded the universe isn't just about what's there, it's also about what isn't and why. Galaxies might seem like lone giants drifting through the void, but they're far more social than we once thought. Picture two majestic spirals, each with hundreds of billions of stars, caught in a gravitational dance that spans millions of years. As they slowly swing past one another, their mutual pull stretches them like cosmic taffy, flinging out ribbons of stars and gas that glow faintly against the darkness. These aren't just random collisions, they're the universe's way of weaving connections across the emptiness, turning isolated islands into a dynamic, interconnected network. Take the Tadpole Galaxy, for example, a stunning snapshot of this process in action. Its long, shimmering tail, stretching over 280,000 light-years, is a testament to the gravitational forces at play. That tail isn't just debris, it's a river of stars and gas stripped away during a close encounter with another galaxy. Over time, these scattered stars might never return to their original home. Instead, they'll linger in the space between galaxies, forming what astronomers call tidal streams, ghostly bridges of light that trace the history of these cosmic interactions. But here's what's truly fascinating. Even galaxies that never collide feel each other's presence. The Andromeda Galaxy, our Milky Way's nearest major neighbor, is already tugging at us, warping the faint outer edges of our galaxy's disk. This subtle gravitational conversation has been going on for billions of years, and in about 4 billion more, it'll culminate in a head-on merger. When that happens, the two galaxies will spiral together, their stars weaving new patterns in the sky, while their supermassive black holes eventually unite in a titanic embrace. These interactions aren't just spectacular to watch, their cosmic recycling programs on a grand scale. When galaxies graze each other, the shockwaves compress gas clouds, triggering furious bursts of star formation. Some of these newborn stars will be flung into intergalactic space, destined to live out their lives far from any galaxy. others might end up in entirely new stellar neighborhoods carried along by the gravitational currents. And then there's the light, the faint, elusive glow of stars drifting between galaxies, untethered from their origins. This intra-cluster light is one of astronomy's most hauntingly beautiful phenomena. It's the combined radiance of countless orphan stars, cast adrift by ancient collisions and now floating freely in the darkness. In dense galaxy clusters, this ghostly glow can outshine all the cluster's galaxies combined, a reminder that even the emptiest spaces hold traces of the universe's turbulent past. Among the countless stars adrift in the vastness between galaxies, there exists a haunting glow so faint that it eluded detection for decades, yet so vast that it holds the secrets of cosmic collisions. This is intra-cluster light, the ghostly aftermath of galaxies tearing each other apart. Picture the scene. As two galaxies spiral into a gravitational embrace, their outermost stars are flung outward like sparks from a bonfire, set adrift in the darkness. These stars no longer belong to any galaxy. Instead, they wander the void, their collective glow a silent testament to the universe's turbulent history. What makes this phenomenon so remarkable isn't just its beauty, it's the clues it carries. By mapping the distribution of this faint light, astronomers can trace the gravitational battles that shaped galaxy clusters over billions of years. Like forensic scientists reconstructing a crime scene, they follow the trails of orphaned stars to uncover ancient mergers, some so violent they reshaped entire regions of space. In the Coma cluster, for example, intra-cluster light reveals a history of relentless collisions, with streams of stars stretching far beyond the cluster's core, a cosmic fingerprint of chaos frozen in time. But here's the twist: these stars aren't just passive relics, they're active participants in the cosmic ecosystem. Freed from the dense environments of their parent galaxies, they're exposed to the harsh conditions of intergalactic space, where temperatures swing wildly and radiation bathes everything in a relentless glow. Yet some still host planets, raising the tantalizing possibility of worlds orbiting these nomad stars, bathed in eternal twilight. Imagine a civilization on such a planet. Their night sky wouldn't be dotted with neighboring stars but dominated by the distant glow of galaxy clusters, a view both breathtaking and isolating. The scale of this phenomenon defies intuition. In some clusters, intra-cluster light accounts for nearly 20% of all visible stars, meaning 1 in every 5 stars exists untethered, floating in the abyss. Recent observations with ultra-sensitive telescopes have even detected individual red giants in these streams, their faint light a beacon across millions of light years. Each one tells a story of ejection, a moment when gravitational forces overcame a star's bond to its home. And yet, for all its grandeur, intra-cluster light is just one piece of the puzzle. Beyond these drifting stars, the voids between galaxies crackle with another kind of wanderer: cosmic rays, particles accelerated to nearly the speed of light, racing through the darkness with enough energy to rival the most violent events in the universe. Flashing through the void at nearly the speed of light, cosmic rays are the universe's ultimate messengers, packing more energy in a single particle than a major league fastball. These aren't your everyday protons and atomic nuclei. They've been accelerated to mind-bending velocities, some carrying the force of a tennis ball traveling at 100 miles per hour. But compressed into a subatomic speck, where do these intergalactic speed demons come from? That's one of astronomy's most enduring puzzles. Some likely originate closer to home, born in the shockwaves of supernova explosions right here in our Milky Way. But the most energetic ones, the real cosmic heavyweights, must have traveled from distant galaxies, their paths twisted by magnetic fields across millions of light years before slamming into Earth's atmosphere. Detecting these particles is like playing detective with the universe's most extreme events. When ultra-high-energy cosmic rays hit our atmosphere, they create cascades of secondary particles. Subatomic fireworks show that scientists can trace back to their likely origins. Some point toward active galactic nuclei, where supermassive black holes spew jets of plasma with enough force to launch particles across intergalactic space. Others might come from colliding galaxies or even more exotic phenomena we haven't discovered yet. The Pierre Auger Observatory in Argentina has spent years mapping these cosmic bullets, revealing an unexpected pattern. Many seem to originate from regions just beyond our local galaxy cluster, hinting at colossal particle accelerators lurking in the cosmic dark. What's truly astonishing is what these particles reveal about the fabric of space itself. The most energetic cosmic rays ever detected carry so much energy that they shouldn't survive the journey to Earth. According to known physics, they should have lost momentum billions of years ago, scattering their energy in collisions with the cosmic microwave background, the faint afterglow of the Big Bang. Yet here they are, defying expectations and forcing scientists to reconsider fundamental assumptions about particle physics. Some theories suggest these ultra-high-energy rays might be evidence of entirely new particles or interactions, cosmic fingerprints of physics beyond our current understanding. But cosmic rays aren't just scientific curiosities, they're part of an invisible ecology that shapes galaxies and even life itself. As these charged particles zip through interstellar and intergalactic space, they help ionize gas, influencing star formation and the chemical evolution of galaxies. Some researchers speculate that cosmic rays bombarding early Earth might have played a role in triggering the molecular changes that led to life. And right now, as you watch this, dozens of these particles are passing through your body, silent reminders that we're all connected to the universe's most violent events across space and time. This interplay between the infinitely small and the cosmically vast brings us to another profound mystery, the quantum fluctuations of the early universe. Imagine the cosmos in its first trillionth of a second, a seething quantum foam where particles blinked in and out of existence, creating microscopic ripples that would one day shape the fate of galaxies. In the first trillionth of a second after the Big Bang, the universe was a seething ocean of quantum foam, a place where particles flickered in and out of existence so quickly they barely had time to leave a trace. Yet these fleeting fluctuations, smaller than a single atom, held the blueprint for everything we see today. Imagine throwing a handful of pebbles into a still pond. The ripples spread outward, growing fainter but never truly disappearing. Now scale that up to cosmic proportions. Those tiny quantum ripples stretched across the entire universe during a period called inflation, when space itself expanded faster than light. What began as subatomic wrinkles became the seeds of galaxies, clusters, and the vast voids between them. The proof is written in the oldest light we can see, the cosmic microwave background, a faint glow from when the universe was just 380,000 years old. This celestial snapshot reveals a patchwork of slightly warmer and cooler spots, each one a fossilized imprint of those primordial density variations. The warmer regions, slightly denser pockets where matter had begun to clump, pulled together by gravity. The cooler spots, the embryos of cosmic voids, where less matter meant less gravitational pull. Over billions of years, these subtle differences snowballed into the universe we recognize today, with galaxies flocking to the denser regions and leaving the voids to stretch emptier and emptier. But here's the astonishing part. Those initial fluctuations were almost perfectly uniform, the temperature differences in the cosmic microwave background. A mere 1 part in 100,000, like a sheet of glass with imperfections so tiny you'd need a microscope to see them. Yet that faint unevenness was enough for gravity to work its magic, amplifying the denser regions until they collapsed into stars and galaxies. It's a cosmic version of the butterfly effect, where microscopic changes in the universe's infancy dictated the placement of every galaxy supercluster we observe now. What caused these fluctuations in the first place? The leading theory points to quantum mechanics, the same physics that governs particles on the smallest scales. During inflation, space expanded so rapidly that quantum jitters got stretched to macroscopic sizes, freezing into the density variations we see today. It's as if the universe's earliest moments were a quantum roll of the dice, and the outcome determined where galaxies would bloom and where darkness would reign. Yet mysteries remain. Why did inflation happen at all? What triggered it and what stopped it? Some theories suggest the inflaton field, a hypothetical energy field that drove this exponential expansion, but its nature is still unknown. Others propose even wilder ideas, like collisions between universes in a multiverse. What we do know is that without these quantum seeds, the cosmos would be a featureless void. No stars, no planets, no life. The very structure of the universe, from the grandest galaxy cluster to the loneliest star adrift between them, owes its existence to whispers in the quantum dark. And now, as we peer deeper into these ancient imprints, we're uncovering clues about the universe's fate. The same fluctuations that birthed galaxies also set the stage for dark energy, the mysterious force accelerating the universe's expansion. By studying their patterns, we might finally answer whether the cosmos will keep stretching forever, or whether gravity will one day pull it all back together. But that's a story for another moment, because right now, there's an even bigger puzzle lurking in the shadows, the invisible scaffolding of dark matter that holds it all together. Dark energy isn't just some abstract concept, it's the universe's most dominant force, silently shaping the fate of everything we see. Imagine blowing up a balloon with tiny dots on its surface. As the balloon expands, the dots don't move themselves, the space between them stretches. That's exactly what dark energy is doing to our cosmos, accelerating the expansion of the universe so that galaxies are being pushed apart faster and faster. But unlike the balloon, there's no outer edge, no boundary, just an endless growing expanse where the very fabric of reality is being stretched thinner by the second. What makes dark energy so baffling is how little we know about it. We can measure its effects, the way distant supernovae appear dimmer than they should, or how galaxy clusters drift apart over time, but its true nature remains one of physics' greatest mysteries. Is it a constant energy woven into space itself, as Einstein once speculated with his cosmological constant? Or could it be something far stranger, like a dynamic field that changes over time, growing stronger or weaker as the universe ages? The answer could rewrite our understanding of gravity, quantum physics, and even the ultimate destiny of the cosmos. One clue lies in the universe's expansion rate. When astronomers first discovered dark energy in the late 1990s, they expected to find the universe's growth slowing down, pulled by gravity's relentless tug. Instead, they found the opposite. The expansion was speeding up, as if some invisible hand had pressed the cosmic accelerator. Since then, measurements have only deepened the puzzle. The Hubble Space Telescope's observations of distant supernovae, combined with data from galaxy surveys and the cosmic microwave background, all point to dark energy making up roughly 68% of the universe's total energy budget. Yet despite its overwhelming influence, it leaves no direct trace we can detect in labs or telescopes. This isn't just academic curiosity. Dark energy's behavior holds the key to the universe's ultimate fate. If it remains a constant force, the cosmos will continue expanding forever, growing colder and darker as galaxies vanish beyond the horizon of visibility. But if it strengthens over time, the outcome could be far more dramatic, a hypothetical Big Rip where even atoms are torn apart by runaway expansion. On the other hand, if dark energy weakens, gravity might regain the upper hand, pulling everything back together in a fiery collapse. Each scenario paints a radically different future, and right now, we're racing to figure out which one awaits us. The hunt for answers is driving some of the most ambitious astronomy projects in history. The Dark Energy Spectroscopic Instrument, or DESI, is mapping millions of galaxies to trace how cosmic structures grow under dark energy's influence. Meanwhile, the upcoming Euclid Space Telescope will study the shapes and distributions of billions of galaxies, searching for subtle distortions caused by this enigmatic force. Even gravitational wave detectors like LIGO could provide indirect clues by measuring how dark energy affects the ripples in spacetime from colliding black holes. Yet for all our tools, dark energy remains a shadow on the cosmic ledger, its presence undeniable, its essence unknowable. Solving this mystery won't just fill a gap in our textbooks. It could reveal entirely new laws of physics hidden in the void between galaxies. And as we peer deeper into that void, we're reminded that the universe's greatest secrets don't always lie in the stars, but in the unseen forces that move them. Deep in the cosmic web, where most galaxies shine with the light of billions of stars, there are ghosts, pale, wispy structures so faint they nearly vanish against the blackness of space. These are ultra-diffuse galaxies, and they defy everything we thought we knew about how galaxies form. Take Dragonfly 44, a galaxy in the Coma cluster. Despite spanning as much space as the Milky Way, it emits less than 1% of the light. If our galaxy were a bustling metropolis, Dragonfly 44 would be a handful of streetlights scattered across an entire continent. What makes these ghostly galaxies so puzzling isn't just their faintness, it's what they're hiding. Observations reveal that many, like Dragonfly 44, are stuffed with dark matter, the invisible glue that holds galaxies together. In some cases, these diffuse giants contain even more dark matter than the Milky Way, yet they've failed to turn that gravitational advantage into stars. It's as if they had all the ingredients for a stellar feast but forgot to light the oven. So how do these cosmic specters exist? One theory suggests they're failed galaxies, regions where dark matter clumped together early in the universe's history, but nearby supernova or black hole outbursts blew away their gas before stars could form in earnest. Another idea paints them as survivors, galaxies that wandered too close to a cluster's violent core and had their stars stripped away by gravitational tides, leaving behind a dark matter skeleton with only a wispy veil of stars. There's even a wilder possibility. Some ultra-diffuse galaxies might be pure dark matter halos, where star formation never started at all, and the few visible stars are interlopers captured from passing galaxies. Yet these faint giants aren't just cosmic oddities, they're keys to understanding galactic diversity. Their existence proves that galaxies don't need to follow a single blueprint. Some blaze with star-forming fury, others fade into quiet obscurity, and a few, like these ghosts, linger in between. By studying them, astronomers are rewriting the story of galactic evolution, revealing a universe far more varied than we ever imagined. And just when we think we've grasped their secrets, ultra-diffuse galaxies surprise us again. Recent discoveries show some aren't just passive drifters, they're actively forming new stars, quietly and sporadically, like embers flaring in the dark. Others lurk in near-total isolation, far from the gravitational tug of clusters, suggesting their faintness isn't always the result of cosmic bullying, but perhaps an alternative path galaxies can take from birth. This diversity hints at a deeper truth. The universe loves experimentation. For every grand spiral or glowing elliptical, there's a ghostly outlier pushing the boundaries of what we call a galaxy. And as our telescopes grow more sensitive, we're finding these faint specters everywhere, floating in clusters, drifting in voids, even orbiting our own Milky Way like cosmic phantoms. They remind us that for all we've learned, the cosmos still holds mysteries that defy our expectations, lurking in the spaces we once thought were empty. But if ultra-diffuse galaxies are the ghosts of the cosmic web, quasars are the fireworks, blazing beacons that can outshine entire galaxies, lighting up the void with their fury. These cosmic lighthouses don't just pierce the darkness, they reveal the hidden structure of the universe itself. Quasars are the universe's ultimate powerhouses, lighthouses so bright they outshine entire galaxies, blazing across billions of light years. At their core lies a supermassive black hole, millions to billions of times the mass of our Sun, feasting on gas, dust, and anything else that strays too close. But unlike their quieter cousins, these black holes don't dine in darkness. As material spirals inward, friction heats it to millions of degrees, creating a swirling disk of plasma so luminous it can be seen clear across the cosmos. What makes quasars truly special isn't just their brilliance, it's what they reveal about the spaces between galaxies. When their light journeys through the intergalactic medium, it doesn't pass through untouched. Atoms in the gas absorb specific wavelengths, leaving behind faint fingerprints in the quasar's spectrum. Like cosmic barcodes, these absorption lines tell astronomers exactly what lies between us and the quasar, how much gas, its temperature, even its chemical makeup. The most distant quasars act like time machines, their light carrying snapshots of the universe when it was just a fraction of its current age. One of the most startling discoveries came from the spectra of ancient quasars. They showed vast reservoirs of ionized helium, evidence that the universe underwent a dramatic transformation known as reionization, when the first stars and galaxies flooded space with ultraviolet light, stripping electrons from atoms and ending the cosmic dark ages. Without quasars, we might never have pieced together this pivotal chapter in cosmic history. But quasars do more than illuminate the past. Their beams also expose the cosmic web's hidden structure. In 2011, astronomers using the Keck Observatory spotted something extraordinary: the glow of intergalactic hydrogen lit up by a quasar's radiation, revealing filaments of gas stretching across millions of light years. It was the first direct glimpse of the universe's hidden scaffolding, proving theories about how matter clumps between galaxies. The sheer power of quasars defies imagination. Some blast out jets of plasma at nearly light speed, carving bubbles in the intergalactic medium that persist for eons. Others flicker unpredictably, their brightness changing in days or even hours, a sign that the chaos around their black holes is unfolding on scales smaller than our solar system. Yet for all their ferocity, quasars are fleeting. Most shine brilliantly for just a few million years before their fuel runs out, leaving behind dormant black holes like the one quietly lurking in our own Milky Way. What's next for these cosmic beacons? New telescopes like the James Webb Space Telescope are peering even further back in time, hunting for the earliest quasars to understand how black holes grew so massive so quickly. Others, like the upcoming Vera C. Rubin Observatory, will scan the skies for rare, changing-look quasars, objects that switch between active and quiet states, offering clues about how black holes flicker to life. Yet for all we've learned, quasars still guard their secrets. How do their black holes grow so fast? What shuts them off? And what role did they play in shaping the galaxies around them? Every answer pulls back another layer of the mystery, revealing just how much we still have to learn about these dazzling monsters of the deep cosmos. And speaking of extremes, if quasars are the universe's raging infernos, the coldest molecules in space are its silent frost, a realm where temperatures plunge to just a whisper above absolute zero. Between the blazing fury of quasars and the ghostly glow of orphan stars, the cosmic void holds another secret: vast clouds of cold molecular gas, drifting like frozen islands in the darkness. These aren't the sparse, scattered atoms of the intergalactic medium. They're dense, frigid nurseries where temperatures plunge just a few degrees above absolute zero, and molecules huddle together in the cold. Finding them out here, far from any galaxy, is like stumbling upon an iceberg in the middle of the ocean, an unexpected clue that the emptiest places in the universe might still be hiding the ingredients for new stars. Some of these clouds could be cosmic fugitives, flung out of their home galaxies during violent collisions or tidal encounters. Picture two galaxies grazing each other, their gravitational dance so chaotic it rips apart giant molecular clouds, sending them careening into the void. Others might be primordial relics, leftover scraps from the early universe that never quite collapsed into galaxies. Their chemistry tells the story: traces of carbon monoxide, formaldehyde, even complex organic molecules, all frozen in the deep cold of intergalactic space. These aren't just random clumps, they're time capsules, preserving the raw materials of star formation in near-perfect isolation. What's truly baffling is how they survive at all. In the harsh environment between galaxies, where radiation bathes everything and matter is stretched thin, these clouds should have evaporated eons ago. Yet here they are, defying the odds. Some might be shielded by dark matter, their invisible halos acting like cosmic bunkers. Others could owe their longevity to sheer size so massive that even over billions of years, they've only lost a fraction of their gas. The most surprising part, a few show signs of slow, quiet star formation, as if the void itself is trying to spark new suns in the dark. These discoveries rewrite what we thought we knew about the cosmic wilderness. It's not just a graveyard of scattered atoms and fading light. It's a dynamic frontier where the building blocks of galaxies still linger, waiting for the right conditions to ignite. And if cold gas can hide in the void, what else might be out there, unseen? That question leads us to one of the universe's most dramatic processes, where galaxies don't just pass gas, they devour each other whole. Galaxies aren't the peaceful islands they appear to be, they're predators. Lurking in the darkness, the largest galaxies grow by consuming their smaller neighbors, a process as brutal as it is beautiful. Take our own Milky Way. Right now, it's tearing apart the Sagittarius dwarf galaxy, stretching its stars into a shimmering river that wraps around our galactic halo. This isn't some rare cosmic event. It's how galaxies evolve, growing through a slow-motion feast that spans billions of years. The mechanics of galactic cannibalism are both elegant and violent. When a smaller galaxy drifts too close to a giant, gravity takes over. The larger galaxy's tidal forces, the same phenomenon that creates ocean tides on Earth, stretch the smaller one like taffy, pulling stars away in long, luminous streams. Some stars are flung into the galactic halo, where they orbit aimlessly like lost travelers. Others settle into new paths, forever marked as outsiders in their adoptive home. The densest parts of the victim galaxy, like its core, often survive longer, sinking toward the center of the predator in a slow death spiral. Astronomers call this hierarchical merging, and it's the universe's way of building cosmic metropolises. The most massive galaxies we see today, like the elliptical behemoth Messier 87, likely grew by devouring dozens of smaller galaxies over eons. Even seemingly peaceful spirals like the Milky Way have violent past. Stellar fossils in our halo tell the story of at least a dozen mergers, with more to come. The upcoming collision with the Andromeda Galaxy, set for 4 billion years from now, will be the ultimate act of galactic cannibalism, reshaping both galaxies into something entirely new. But the evidence isn't just in the stars. Dark matter, the invisible scaffolding of galaxies, betrays these ancient meals too. When galaxies merge, their dark matter halos intertwine, leaving behind distorted gravitational fingerprints. By mapping these distortions, astronomers can reconstruct merger histories like cosmic archaeologists, uncovering tales of destruction written in the warp and weave of spacetime itself. And then there are the orphan planets torn from their parent stars during these mergers, set adrift in the darkness. These rogue worlds, no longer bound to any solar system, wander the void between stars, frozen and alone. Some might outnumber stars in our galaxy by 100 to 1, a hidden population of nomads forged in the chaos of galactic collisions. Their existence hints at a universe far more dynamic and interconnected than we ever imagined, where even the smallest worlds can become casualties in the grand dance of cosmic consumption. Imagine a planet untethered from any star, drifting through the eternal night of intergalactic space. No sunrise, no sunset, just endless darkness stretching in every direction. These are rogue planets, cosmic nomads cast adrift by gravitational chaos, and they might be the most common worlds in the universe. Astronomers estimate billions, perhaps even trillions, of these lone wanderers could exist in our galaxy alone, outnumbering stars by a staggering margin. Some were born in the turbulent nurseries of young star systems, only to be flung into the void by gravitational slingshots. Others might have formed in isolation, condensing directly from cold clouds of gas in the deepest voids, never knowing the warmth of a sun. Detecting these ghostly worlds is like searching for a single candle flickering in a foggy desert. Without a host star to illuminate them, they're virtually invisible, except for the faint heat signature they emit. That's where future telescopes like NAS and Nancy Grace Roman Space Telescope come in. Designed to scan the skies in infrared, it could spot the dim glow of rogue planets, revealing their temperatures, sizes, and even atmospheric compositions. Some might be frozen wastelands, their surfaces colder than Pluto, while others could harbor hidden oceans beneath icy crusts, kept liquid by internal heat or radioactive decay. What's truly mind-bending is the possibility that some rogue planets might not be alone. Theoretical models suggest they could retain moons, captured during their violent ejection or formed alongside them. Picture a frozen world with a single, tiny moon, a duo wandering the cosmos together, a flicker of companionship in the infinite dark. Some scientists even speculate about the potential for life on these outcasts, sustained by geothermal vents or subsurface oceans, though it would be a lonely existence under an eternal starless sky. The existence of rogue planets forces us to rethink what a planetary system can be. We're used to neat diagrams with planets orbiting stars, but the universe is messier and far more creative. Planets don't need stars to exist, and they might thrive in the most unexpected places, from the bustling galactic center to the frigid voids between galaxies. Every rogue planet we discover is a reminder that the cosmos refuses to fit neatly into our models, always surprising us with its boundless variety. And now, as we peer deeper into the cosmic tapestry, we encounter another relic of the universe's infancy, the cosmic microwave background, a whisper of light from the dawn of time. This ancient glow holds the secrets of how everything began, from the first quantum ripples to the vast structures we see today. The cosmic microwave background isn't just ancient light, it's the universe's first baby picture, a snapshot frozen in time when the cosmos was just 380,000 years old. Picture the universe back then, not black and empty, but a glowing sea of plasma, hot and dense as the surface of a star. As it expanded and cooled, atoms finally formed, releasing a burst of light that's been traveling ever since, stretched by the expansion of space into the faint microwave hum we detect today. This afterglow isn't confined to some far-off region. It fills every cubic centimeter of the universe, including the space around you right now. Tune an old analog television to static, and about 1% of that snowy interference comes from this primordial radiation, literally echoing the birth of everything. What makes this glow so revolutionary isn't just its age, it's the secrets encoded in its subtle imperfections. To the naked eye, the cosmic microwave background looks perfectly uniform, like a featureless fog. But when scientists map it with instruments like the Planck satellite, they discover a tapestry of tiny temperature variations, some spots slightly warmer, others cooler by just a few millionths of a degree. These fluctuations are the universe's genetic code, the seeds from which galaxies, clusters, and cosmic voids would later grow. The warmer patches slightly denser regions where gravity would eventually pull matter into galaxies. The cooler spots, the embryos of today's vast cosmic deserts, like the Bowotes void. It's staggering to think that the grand structures we see around us, the glittering cities of stars, the yawning gaps between them, all trace back to these microscopic ripples in the newborn cosmos. But the cosmic microwave background does more than reveal the universe's structure. It's also a precision tool for measuring its ingredients. By analyzing the patterns in this radiation, astronomers can calculate the exact mix of ordinary matter, and dark energy with unprecedented accuracy. The results are humbling. The atoms making up stars, planets, and us account for just 5% of the cosmos. Dark matter, invisible and mysterious, makes up 27%, while dark energy, driving the universe's accelerating expansion, dominates at 68%. These numbers aren't guesses, they're etched into the cosmic microwave background's subtle undulations, a cosmic ledger we're still learning to read. One of the most profound revelations from this ancient light is the universe's geometry. The way temperature variations are distributed across the sky tells us space itself is flat, not in the everyday sense, but in the grand, relativistic meaning. Parallel lines stay parallel forever, and the angles of a triangle always add up to 180 degrees. This flatness hints at something extraordinary. The universe's total energy density is perfectly balanced, a Goldilocks condition that only makes sense if the early cosmos underwent a mind-boggling growth spurt called inflation, expanding faster than light in the first fraction of a second. Without inflation, those faint temperature variations wouldn't align with what we observe, and the cosmic microwave background becomes our strongest evidence that this wild theory might just be true. Yet for all its answers, this primordial glow still holds mysteries. Some large-scale patterns in the data don't quite match predictions, like the infamous cold spot, a strangely chill region that might be a statistical fluke or evidence of something stranger, like a collision with another universe in the multiverse. Other anomalies suggest the cosmos might not be perfectly uniform in all directions, a potential crack in our assumption that the universe looks the same no matter where you're standing. These oddities keep scientists digging because every discrepancy could be a clue to physics beyond our current understanding. And then there are the shadows, the faint imprints left by particles that barely interact with light at all. Neutrinos, those ghostly subatomic particles streaming through you by the trillions every second, left their mark on the cosmic microwave background as they fled the hot plasma of the early universe. Their subtle pressure waves altered the radiation's patterns in ways we can now measure, giving us a window into conditions so extreme they make the core of the Sun seem tame. These cosmic fingerprints remind us that the universe's story isn't written solely in light. It's etched into the dance of particles we're still learning to see. So the next time you hear static on the radio, take a moment to listen not just to the noise, but to the whisper of creation itself, a message from a time before stars, before galaxies, when the entire universe could fit in a realm smaller than an atom. And as we turn our gaze to the voids between galaxies, remember, even in the emptiest places, the echoes of that explosive beginning still resonate, shaping the cosmos in ways we're only beginning to comprehend. Every second, trillions of invisible cosmic ghosts pass straight through your body, not some metaphor, but real subatomic particles called neutrinos. Born in the nuclear furnaces of stars, the violent deaths of supernovae, and even the Big Bang itself, these elusive phantoms are the universe's ultimate escape artists. With no electric charge and barely any mass, they slip through planets like they're not even there. A single neutrino could travel through a light year of solid lead without bumping into a single atom. Yet despite their ghostly nature, these particles are everywhere. The Sun alone showers Earth with 65 billion neutrinos per square centimeter every second. Hold your hand up to the light for just 1 second, and more neutrinos pass through it than there are stars in the Milky Way. Why does something so intangible matter? Because neutrinos are cosmic witnesses, carrying unfiltered stories from the universe's most extreme environments. When a star collapses into a supernova, 99% of its energy bursts out as neutrinos, a flash so intense it outshines all the stars in the galaxy combined. In 1987, detectors on Earth caught neutrinos from a supernova in the Large Magellanic Cloud hours before the light arrived, proving these particles could give us early warnings of stellar explosions. Even more mind-bending are the relic neutrinos left over from the Big Bang, still drifting through space after 13.8 billion years. These ancient particles are like fossils from the universe's first second, holding clues about how everything began. Yet detecting them is like trying to catch smoke with your bare hands. Most neutrino observatories are engineering marvels, giant tanks of ultra-pure water or liquid argon buried deep underground to shield from other particles. When the rare neutrino does interact, it creates a flash of light or a charged particle that sensors can pick up. The Ice Cube Neutrino Observatory in Antarctica uses an entire cubic kilometer of glacial ice as its detector, searching for the faint blue glow produced when a neutrino collides with an atom in the ice. In 2013, it made history by detecting neutrinos from outside our galaxy, some likely hurled at us by supermassive black holes or colliding galaxies. But here's the twist: neutrinos might be shaping the cosmos as much as they're observing it. Their tiny mass, once thought irrelevant, could collectively influence how galaxies cluster through gravity. Some theories even suggest neutrinos played a role in why matter dominates over antimatter in the universe, solving one of physics' biggest mysteries. And if that's not strange enough, there are hints that neutrinos might oscillate between different types as they travel, a quantum quirk implying they have mass after all, challenging the standard model of particle physics. Now imagine if life could exist in the vast voids between galaxies. It sounds like science fiction, but the universe has surprised us before. Floating in the darkness, far from any star, rogue planets with subsurface oceans might harbor extremophile organisms. Or consider microscopic life drifting on dust grains, powered by cosmic rays instead of sunlight. The building blocks of life, organic molecules, have been found in meteorites and interstellar clouds, so why not in the intergalactic medium? Some theorists even propose that advanced civilizations might harness dark energy to traverse these deserts, using physics we've yet to discover. While evidence remains speculative, the sheer scale of the cosmos suggests that if life can find a way, it will, no matter how hostile the environment seems. After all, on Earth, we've found microbes thriving in nuclear reactors, acidic hot springs, and the crushing depths of the Mariana Trench. The universe, it seems, is far more creative than we are. Could life exist in the unimaginable vastness between galaxies where temperatures swing from near absolute zero to millions of degrees, and radiation bathes everything in a relentless glow? At first glance, the idea seems impossible. Yet Earth's own extremophiles microbes thriving in boiling hydrothermal vents, frozen Antarctic lakes, even the radioactive ruins of Chernobyl prove life can adapt to conditions once thought unsurvivable. If organisms can flourish in these hostile pockets of our planet, could the cosmos harbor its own interstellar nomads, drifting far beyond the warmth of any star? One tantalizing possibility lies with rogue planets, those orphaned worlds ejected from their star systems during gravitational chaos. Imagine a frozen exoplanet, its surface a perpetual nightscape, but beneath miles of ice, geothermal vents, or radioactive decay maintaining a subsurface ocean. On Earth, entire ecosystems thrive around similar vents, powered not by sunlight but by chemosynthesis. In the void between galaxies, such a world could drift for billions of years, its hidden oceans sheltering microbes or even complex life, utterly isolated from the rest of the universe. Some calculations suggest rogue planets might outnumber stars in the Milky Way by 100 to 1. If even a fraction hosts subterranean oceans, the cosmic wilderness could be teeming with invisible biospheres. But life might not need a planet at all. Intergalactic space, though mostly empty, isn't completely barren. Microscopic dust grains, organic molecules, and even water ice float between galaxies, remnants of ancient stellar explosions or planetary collisions. On Earth, bacteria have survived for years in the vacuum of space aboard the International Space Station, shielded only by thin layers of rock or ice. Could similar organisms hitchhike on cosmic dust, riding the faint currents of radiation pressure or magnetic fields? It's a stretch, but not impossible, especially if life can enter a dormant state like Earth's tardigrades, reviving when conditions improve. Then there's the wild card, dark matter. We still don't know what it's made of, but some theories suggest it could interact in ways we haven't discovered. If dark matter particles occasionally collide and release energy, could they provide a faint, universal heat source? Or if dark matter structures shield pockets of gas from radiation, might they create unexpected oases in the void? These are fringe ideas, but in a universe where 95% of everything is invisible and unknown, ruling anything out feels premature. Of course, the biggest hurdle is energy. Without sunlight or geothermal vents, how could life sustain itself? Cosmic rays, high-energy particles zipping through space, might offer a clue. On Earth, certain bacteria can harness radiation for energy in a process called radiosynthesis. In the void where cosmic rays are abundant, extremophiles could theoretically evolve to exploit them, turning a lethal hazard into a lifeline. Alternatively, chemical reactions in molecular clouds, slow as they are, might provide just enough energy over millennia to sustain dormant organisms. The deeper we look, the more the universe surprises us. From methane lakes on Titan to the subsurface oceans of Europa, environments once deemed sterile now seem like potential havens. If life can cling to existence in these niches, why not in the vast tracts between galaxies? The distances are staggering, the conditions brutal, but life, as we've seen, is relentless. And if life does exist out there, how would we ever find it? Traditional telescopes can't spot a microbe on Pluto, let alone a rogue planet light years away. Future missions might look for biosignatures in intergalactic dust or anomalies in the spectra of distant quasars. Or perhaps one day, a probe drifting between galaxies will stumble upon an impossible signal, a molecular structure too complex to have formed by chance. This isn't just speculation, it's a challenge to our imagination. Every time we've declared a corner of the universe uninhabitable, from deep sea trenches to acid clouds, life has proven us wrong. The void between galaxies may be the ultimate frontier, but if there's one lesson astrobiology teaches us, it's this: life finds a way. Now, let's shift from the mysteries of biology to the audacious dreams of engineering, because if humans ever hope to cross these unimaginable distances, we'll need more than rockets. We'll need to rethink physics itself. Crossing the void between galaxies isn't just a challenge, it's a humbling reminder of how vast the cosmos truly is. Even our fastest spacecraft, like NASA Parker Solar Probe, which streaks through space at over 400,000 miles per hour, would take thousands of years just to reach the nearest star, let alone another galaxy. The Andromeda Galaxy, our closest galactic neighbor, floats 2.5 million light-years away. At that distance, with today's technology, a one-way trip would last longer than human civilization itself. But what if we refuse to accept those limits? What if the same curiosity that propelled us from wooden ships to moon landings could someday bridge the intergalactic abyss? Theoretical physics offers a few tantalizing possibilities, concepts so advanced they blur the line between science and science fiction. Take warp drives, for example. Popularized by franchises like Star Trek, these hypothetical engines wouldn't move a ship through space conventionally. Instead, they'd manipulate space-time itself, compressing it in front of the vessel and expanding it behind, effectively surfing on a wave of distorted reality. While this sounds like pure fantasy, the math behind it traces back to Einstein's general relativity. Miguel Alcubierre's 1994 paper showed that, in theory, such a warp bubble wouldn't violate the laws of physics, though it would require exotic matter with negative energy, something we've yet to discover. Even if possible, the energy demands could exceed the total output of a star, turning a galactic joyride into a civilization-spanning project. Then there's the slower, more sobering alternative: generation ships. These would be massive, self-sustaining arcs carrying entire communities across millennia, with each new generation born, living, and dying aboard the vessel until their descendants finally reached another galaxy. Imagine a floating world with farms, schools, and ecosystems, all engineered to endure the loneliness of deep space. The challenges are staggering: maintaining morale over centuries, preventing genetic bottlenecks, surviving cosmic radiation. But unlike warp drives, generation ships don't rely on undiscovered physics. They're a test of societal will as much as engineering, requiring a level of long-term planning humanity has never attempted. Yet before we even dream of propulsion, we'd need to survive the journey itself. The space between galaxies isn't just empty, it's a gauntlet of cosmic rays, extreme temperatures, and near-total isolation. Shielding a ship from radiation might require magnetic fields stronger than anything we've built, or layers of water and ice meters thick. And with no stars nearby for refueling, missions would need to harness fusion or antimatter, technologies still in their infancy. Even communication would lag. A message sent from a ship halfway to Andromeda would take over 1 million years to reach Earth, rendering real-time contact impossible. The sheer scale of intergalactic travel forces us to confront deeper questions, not just about engineering, but about our place in the universe. Would a species capable of such journeys still resemble humanity as we know it? After millennia in transit, cultures might evolve beyond recognition, their original mission fading into myth and what would await them upon arrival. By the time a generation ship reached Andromeda, the galaxy itself would have changed, its stars shifting positions over millions of years. For now, these ideas remain thought experiments, stretching our imagination to its limits. But history shows that today's impossibilities often become tomorrow's breakthroughs. The same cosmic voids that seem impassable today might one day be highways if we're bold enough to reimagine the rules. And as we peer into that darkness, we're reminded that the greatest journeys begin not with engines or equations, but with a single question: what if? Now, let's turn from the distant future to the ultimate fate of the cosmos itself, because whether we reach other galaxies or not, the universe has its own expiration date. The universe won't end with a bang or a whimper, but with an endless, silent freeze. Picture a cosmic landscape trillions of years from now, where the last stars have flickered out like dying embers and galaxies have evaporated into darkness. Space itself, once vibrant with light and motion, becomes a graveyard of exhausted energy, where even black holes, the universe's most resilient survivors, have finally evaporated into faint whispers of radiation. This is the heat death, the ultimate triumph of entropy, where every difference in temperature, every potential for work or change, has been smoothed into a uniform, lifeless chill. The science behind this chilling fate comes straight from thermodynamics. Just as a cup of coffee left untouched will eventually match the temperature of the room, the universe is destined to reach equilibrium. Stars, those brilliant engines of fusion, will exhaust their fuel. Galaxies, bound by gravity, will unravel as dark energy pushes them apart faster than any signal can bridge the gap. Even the protons that make up atoms, once thought indestructible, may decay over unimaginable timescales, reducing all matter to a thin haze of subatomic particles drifting in the void. The cosmos, in its final act, becomes a static sea of near absolute zero, where nothing happens forever. Yet this grim outcome isn't the only possibility. Some theories suggest a more dramatic finale, the Big Rip. If dark energy grows stronger over time, it could eventually overpower every force holding the universe together. Galaxies would tear apart first, then stars, then planets, until finally, even atoms are ripped asunder in a catastrophic crescendo. Alternatively, a big crunch could await us, where gravity finally overcomes dark energy's push, reversing the expansion and collapsing everything back into a singularity, a cosmic reset button that might trigger another Big Bang. Then there's the wild card, vacuum decay. Imagine the universe's fundamental fields are like marbles resting in a valley. Right now, they're stable, but if some quantum fluctuation nudged them into a lower energy state, it could create an expanding bubble of true vacuum, where the laws of physics rewrite themselves. Light, matter, even time could behave differently inside, effectively erasing the universe as we know it in a wave of annihilation moving at the speed of light. The heat death might seem inevitable, but so did many things before science revealed deeper layers. Quantum mechanics, dark energy, and the nature of space-time are still full of mysteries. Perhaps future discoveries will unveil escape hatches, wormholes to new universes, quantum resurrection, or cycles of rebirth we can't yet imagine. For now, the heat death stands as a reminder of the universe's fragility, and the astonishing fact that we're here at all, in this brief golden age where stars still shine and curiosity burns brighter than the void. Dark energy isn't just stretching the cosmos, it might be writing its final chapter. While the heat death of the universe is the most widely accepted fate, there are two other possibilities that rewrite the rules of reality itself. The first, the Big Rip, is cosmic demolition on the grandest scale. Imagine dark energy growing stronger over time, its repulsive force accelerating until it doesn't just push galaxies apart, it tears them apart. First, galaxy clusters would unravel, their gravitational bonds no match for the escalating force. Then, individual galaxies would disintegrate, stars ripped from their orbits like leaves in a hurricane. Finally, in the last horrific moments, planets, molecules, even atoms would be shredded into fundamental particles, space itself rupturing at the seams. Time would lose all meaning as the universe fractures into infinite, disconnected voids. On the opposite end of the spectrum lies the Big Crunch, a dramatic reversal of cosmic expansion. If dark energy weakens or gravity somehow regains dominance, the universe's outward rush could slow, halt, and then reverse. Galaxies would begin careening back toward one another, their light blue shifting as space contracts. Temperatures would rise, first melting icy moons, then vaporizing planets, until the entire cosmos becomes a seething furnace. In the final moments, all matter would collapse into a singularity, a mirror image of the Big Bang, where space, time, and the laws of physics as we know them cease to exist. Some theories even suggest this singularity could trigger a new Big Bang, birthing another universe in an endless cycle of creation and destruction. The key to which fate awaits us lies in dark energy's mysterious nature. Is it a constant force, as Einstein's cosmological constant suggests, or does it evolve, growing stronger or weaker over time? Observations of distant supernovae and galaxy clusters hint that dark energy's density might be increasing, favoring the Big Rip scenario. But the margin of error is still too wide to rule out a Big Crunch or even a third, undiscovered possibility. What's certain is that both outcomes force us to confront the fragility of reality. In a Big Rip, the very fabric of spacetime is mortal. In a Big Crunch, time itself has an expiration date. These aren't just abstract thought experiments, they shape how we understand the universe's architecture. If the Big Rip is inevitable, then the cosmic web's filaments are temporary scaffolds, destined to snap. If the Big Crunch looms, then galaxy collisions aren't just occasional events but previews of a universal collapse. Even the voids between galaxies, those seemingly eternal deserts, would vanish in either scenario, stretched into oblivion or crushed into non-existence. Simulations are our best window into these apocalyptic futures. Supercomputers model dark energy's behavior under different assumptions, tracing how galaxy clusters disperse or converge over billions of virtual years. Some recreate the Big Rip down to the quantum level, showing how phantom energy, a hypothetical extreme form of dark energy, would unravel atomic nuclei. Others simulate the Big Crunch's fiery collapse, revealing how black holes might merge in the universe's final seconds. These digital experiments don't just predict doom, they help us test the limits of physics itself. If a simulation's black holes evaporate too quickly or dark energy behaves unexpectedly, it could hint at new laws waiting to be discovered. Yet for all their power, simulations can't yet tell us which fate is real. That answer lies in observations mapping more supernovae, measuring the cosmic microwave background's faintest fluctuations, or catching gravitational waves from collisions in the early universe. Each dataset is a puzzle piece, and we're still assembling the edges. One day, the picture might reveal whether we're headed for a rip, a crunch, or something stranger. Until then, the universe keeps its ultimate secret, reminding us that even in its dying moments, it has the power to astonish. And speaking of simulations, they're not just forecasting the end, they are also helping us decode the here and now, revealing how the voids between galaxies shape the universe's past, present, and future. Supercomputers are the universe's time machines, not by bending space-time, but by crunching numbers at speeds that defy comprehension. Picture a simulation so vast it recreates billions of years of cosmic evolution in weeks, tracing the journey of dark matter from a near-uniform haze to the intricate cosmic web we see today. These aren't just video game graphics, they're precision experiments testing how well our theories match reality. Take the Illustris TNG project, for example. This simulation tracks not just the gravitational dance of dark matter, but the complex interplay of gas, stars, and black holes across a virtual universe a billion light-years wide. The result, a breathtaking digital cosmos where spiral galaxies form with stunning realism, and supermassive black holes sculpt their surroundings with jets of energy predictions that align eerily well with telescope observations. But the real magic happens when simulations surprise us. In the Eagle project, researchers noticed something unexpected. Their virtual galaxies produced the right mix of spiral and elliptical shapes only when they accounted for energy from supermassive black holes. Without those black hole feedback mechanisms, galaxies grew too massive too fast, ending up as bloated, unrealistic giants. It's a cosmic balancing act, one that simulations revealed long before telescopes could confirm it. Now, when astronomers observe real galaxies with overactive black holes, they see the same suppression of star formation, proving these digital universes are more than just pretty models. They're guides to physics we can't yet observe directly. What's truly revolutionary is how these simulations handle scale. The Millennium Run, one of the most ambitious cosmic models ever created, simulated over 10 billion particles representing dark matter clumps, each with the mass of a small galaxy. As gravity worked its magic over virtual eons, those particles assembled into a cosmic web strikingly similar to the one mapped by galaxy surveys. But here's the catch: simulations can't just match what we see, they have to predict what we don't. When astronomers discovered the universe's expansion was accelerating, simulations like Bolshoi-Planck recalibrated, adding dark energy to their equations. The result, virtual voids grew larger, galaxy clusters spread farther apart, and the models suddenly aligned with new observational data. Yet for all their power, simulations have limits. They rely on approximations, simplifying equations to make computations feasible, or using subgrid physics to represent small-scale events like supernovae that would otherwise overwhelm even the fastest supercomputers. Sometimes these shortcuts lead to discrepancies, like galaxies forming in the wrong places or gas cooling too quickly. That's where the real scientific detective work begins. Each mismatch is a clue, pointing either to flaws in our theories or gaps in our understanding. When the Virtual Observatory project found that simulated galaxies were less clustered than real ones, it hinted at unseen forces, perhaps new dark matter interactions or primordial magnetic fields waiting to be discovered. The future of cosmic simulations is even more mind-bending. Next-generation projects aim to combine dark matter dynamics with quantum-scale physics, modeling everything from the first stars to the birth of planets. Meanwhile, machine learning is revolutionizing the field, training AI to spot patterns in simulations that humans might miss. Imagine an algorithm sifting through petabytes of virtual universes, flagging anomalies that could lead to breakthroughs in dark energy or particle physics. But simulations alone aren't enough, they need real-world counterparts. That's where upcoming telescopes like the Vera-C, Rubin Observatory, and the Nancy Grace Roman Space Telescope come in. With cameras capable of mapping billions of galaxies, these instruments will test simulations with unprecedented precision, revealing whether our digital universes truly mirror reality. Will they confirm our models or unveil entirely new cosmic mysteries? Either way, the synergy between silicon and starlight is rewriting the story of the cosmos, one calculation at a time. Right now, humanity is building the ultimate cosmic detectives, telescopes so powerful they'll transform the voids between galaxies from blank spaces into rich tapestries of discovery. The James Webb Space Telescope, with its infrared eyes, is already rewriting the rules. Imagine it spotting the faint glow of gas clouds so diffuse they've been invisible until now, or picking out the heat signatures of rogue planets drifting in the darkness. But Webb is just the beginning. The Square Kilometre Array, a radio telescope network spanning continents, will map the universe in wavelengths we've barely explored, tracing the magnetic fields that thread through the cosmic web like invisible highways. Together, these instruments will turn the void into a living laboratory, revealing processes we've only theorized about until now. What makes these telescopes revolutionary isn't just their sensitivity, it's their ability to connect the dots across cosmic history. Take the mysterious warm-hot intergalactic medium, the WHIM, which might hold the universe's missing baryons. Webb's spectrographs can analyze the light from distant quasars as it passes through these filaments, decoding their chemical composition like a cosmic barcode. Meanwhile, the SKA's radio antennas will detect the faintest whispers of hydrogen, the universe's most abundant element, tracing how it's distributed across the voids. For the first time, we'll have a 3D map of the invisible scaffolding that binds galaxies together, and with it, clues about how dark energy and dark matter sculpt the cosmos. But the surprises won't stop there. These telescopes could uncover galaxies so faint they've been hiding in plain sight, or catch magnetic fields shaping gas clouds into structures we never predicted. There's even a chance they'll spot the elusive signatures of primordial black holes, leftovers from the Big Bang that might lurk in the void. Every new observation will test our theories, pushing cosmology closer to answers about the universe's birth, evolution, and ultimate fate. Yet beyond the science, these missions force us to confront a humbling truth. The same voids we once dismissed as empty aren't just voids, they're archives holding the story of everything. And as we decode them, we're not just exploring space, we're discovering our place in a universe far grander, stranger, and more interconnected than we ever imagined. From the tiniest quantum ripples to the largest structures in existence, we're part of this cosmic tapestry, not just observers, but participants in an epic still unfolding. The universe shouldn't work, at least not for us. Every fundamental constant, from the strength of gravity to the mass of an electron, exists in a razor-thin balance. Alter anyone by even a fraction, and stars wouldn't ignite, atoms would fly apart, or matter itself would collapse into nothingness. Yet here we are, in a cosmos where carbon forms in stellar furnaces, water stays liquid across a narrow, life-friendly range, and planets orbit at just the right distance to cradle biology. This eerie precision is the heart of the anthropic principle, the idea that the universe's laws appear inexplicably tailored for life. But is this fine-tuning a cosmic coincidence or something deeper? Take gravity, for instance. If it were slightly stronger, stars would burn too hot and fast, scorching any chance for life to evolve. Too weak, and matter would never clump into galaxies at all. The cosmological constant, which governs dark energy's push against gravity, is even more perplexing. Calculations show its value should be wildly larger, yet if it were, space would expand so violently that no structures could form. Instead, it's balanced on a knife's edge, allowing galaxies to coalesce without collapsing back on themselves. Even the neutron, a seemingly mundane particle, has a mass so precise that if it varied by less than 2%, protons couldn't bond into the atoms that build planets, people, and everything in between. This precision isn't limited to physics. Chemistry, too, depends on cosmic serendipity. Carbon, the backbone of life, forms in stars through a rare resonance, a nuclear coincidence so unlikely that physicist Fred Hoyle famously predicted its existence based on the sheer necessity of its role. Oxygen, water, even the DNA helix, all rely on quantum interactions so delicate they seem almost choreographed. The universe doesn't just permit life, it practically insists on it, with laws that feel less like random settings and more like a carefully tuned recipe. But how do we explain this? One camp argues for the multiverse, a vast ensemble of universes, each with different constants, where we simply inhabit the rare one where everything lines up. In this view, fine-tuning is an illusion. With infinite variations, some universes were bound to hit the jackpot. Others see design, whether divine or emergent, pointing to the sheer statistical improbability of so many independent factors aligning by chance. Then there's the provocative notion that universes capable of observation inevitably select for life-friendly conditions, a cosmic version of survivorship bias. The debate spills beyond science into philosophy. If the universe is fine-tuned, does that imply purpose? Or is it simply a brute fact, no more meaningful than the Earth's distance from the Sun? For some, the anthropic principle humbles us, revealing how fragile our existence is. For others, it elevates our place in the cosmos, suggesting we're not just accidental stardust but witnesses to a deeper order. What's undeniable is how this principle reframes our search for meaning. Whether through multiverses, metaphysics, or sheer luck, the universe's laws invite us to ask not just how things work, but why they work so perfectly for us. And as we peer deeper into the quantum code of reality, each discovery, or lack thereof, brings us closer to answering whether this fine-tuning is the universe's greatest coincidence or its most profound secret. We've traveled through the unimaginable stretches between galaxies, peeling back layers of darkness to reveal a cosmos teeming with invisible forces and untold stories. What we once called empty space is actually a dynamic frontier, where dark matter weaves its unseen web, where ghostly galaxies drift like cosmic phantoms, and where particles thinner than a whisper hold the secrets of the universe's birth. Every discovery in these voids has rewritten our textbooks, proving that the greatest mysteries don't always hide in the light of stars, but in the profound silence between them. Think about how far we've come. A century ago, astronomers debated whether anything existed beyond the Milky Way. Today, we map the cosmic web's filaments with supercomputers, trace the faint glow of orphan stars, and listen for the whispers of dark energy accelerating the universe's expansion. The voids have taught us humility, showing how little of reality we can see with our eyes alone. They've also revealed astonishing connections, like how supermassive black holes regulate galaxy growth from millions of light years away, or how the atoms in your body might have once drifted through intergalactic space before joining your DNA. Yet for all we've uncovered, the deepest questions remain. What exactly is dark matter? Why does dark energy dominate the cosmos? Could life persist in the icy depths between galaxies? These aren't just scientific puzzles, they're invitations to keep exploring, to push our telescopes and imaginations further. The next breakthroughs might come from a teenager analyzing telescope data online, an engineer designing a new detector, or an artist whose vision sparks a radical new theory. So as we conclude this journey, remember, the void isn't emptiness. It's the universe's canvas where the boldest ideas meet the hardest evidence. Whether you're gazing at the night sky or pondering the latest cosmic mystery, you're part of this grand exploration. The story of the spaces between galaxies is still being written, and every curious mind holds a pen. Until our next adventure among the stars, keep looking up, questioning deeply, and marveling at how much wonder fits into what we once mistook for nothing.